Chemistry Standard 12 Solid State Part 5. In this part, we will learn about the magnetic properties of the solid. In a solid, when we are talking about the electron has a two type of motion. You can see in this diagram, one electron is there and this is a nucleus, and electron, it is revolving around the nucleus, and this motion, it is known as its orbital motion, and due to this motion, the magnetic moment which is associated with this electron, that is known as orbital magnetic moment. The second motion of electron, that is, here you can see the motion, electron will revolve on its own axis, and that is spin on its axis, that is called spin moment, and due to this spin moment of electron, it has a spin magnetic moment, and due to this two type of moment, orbital magnetic moment and spin magnetic moment, it will behave like a tiny loop or magnetic loop, and that's why the electron will have the magnetic property, and ultimately the solids will also have the magnetic property in them. And now we will study these properties in detail. Magnetic properties. Every substance has some magnetic properties associated with it. The origin of this property lies in the electron. Each electron in an atom behave like a tiny magnet. Its magnetic moment originate from two type of motion. Its orbital motion around the nucleus and its spin around its own axis. Just now we have studied two type of motion. One is the orbital motion and one it is the spin, or on its axis the motion is there. Electron being a charged particle and undergoing these motions can be considered as a small loop of current which possess a magnetic moment. Thus, each electron has a permanent spin and an orbital magnetic moment associated with it. Magnitude of this magnetic moment is very small and it's measured in unit called Bohr magneton, or you can say mu b. It is equal to 9.27 10⁻⁻24 ampere meter square. On the basis of their magnetic property, substance can be classified into 5 categories. Number 1, that is a paramagnetic substance. Number 2, diamagnetic, ferromagnetic, antiferromagnetic, and ferrimagnetic substance. And we will study all this in detail. Number 1, that is paramagnetism. Paramagnetism substance are weakly attracted by a magnetic field. It means when such type of substance are kept in the magnetic field, they are going to be weakly attracted by this magnetic field. They are magnetized in magnetic field in the same direction. They lose their magnetism in the absence of magnetic field. If we will keep the magnetic field, they will be magnetized, and as we remove the magnetic field, their magnetism will be lost, or they don't have magnetism in the absence of magnetic field. Paramagnetism is due to the presence of one or more unpaired electron which are attracted by the magnetic field, like O2, Cu plus 2, Fe plus 3 and Cr plus 3 are the some example of such type of substance. Here you can have paramagnetic, so one thing we have to keep it in mind, due to the presence of one or more unpaired electron, at least the substance should have one or more unpaired electron. So copper, in the next slide we will see the Cu plus 2, Fe plus 3 and Cr plus 3, all the ions that show the paramagnetism. And O2, if you have remembered in 11th standard, we have learned about the O2 which has a even number of electron, but then also it will show the paramagnetic character due to the molecular orbital theory. The last two electron will be unpaired and it will show the paramagnetism. But in this copper and iron and chromium, they will have the odd number of electron, you can say, and that's why they will have the one unpaired electron and one or more than one unpaired electron, and they will show paramagnetism. You can have here the diagram. First we will take iron. Iron, that is Fe, atomic number is 26. Electronic configuration will be argon, 4s2, 3d6. So here when we make a Fe to Fe plus 2, means we remove the 2 electron. The 2 electron is going to remove from 4s. So electronic configuration will be argon, 4s0 and 3d6. If you remove the 3 electron, so 2 electron from s and 1 electron from 3d. So it will become 4s0 and 3d5. 3d5 means d as having a 5 orbital, and according to the Hund's principle, in each orbital 1 electron will be there. So the maximum number of unpaired electron will be here 5, and that's why it will show the paramagnetic character. In the same way, which we have taken a copper one also. So here also you can see copper plus 2 ion, 3d9. 3d9 means 2 electron are going to be paired and one last electron will be unpaired, and because of this unpaired electron, the paramagnetic character will be present in Cu plus 2 and in other ones also. Dimagnetism, one thing we have to keep it in mind in dimagnetism, generally all the electrons are paired, means there is an even number of electron in that, so that substance will behave as a dimagnetism. Dimagnetic substances are weakly repelled by a magnetic field, like H2O, NaCl and CC6H6 are some examples of such substance. They are weakly magnetized in a magnetic field in opposite direction. Dimagnetism is shown by those substances in which all the electrons are paired and there are no unpaired electrons. Pairing of electron cancel their magnetic moment and they lose their magnetic character. And this last 3 lines are very important. What we have to remember here is all the electrons are paired, there is no unpaired electron, and all the electrons are paired, so they will cancel their magnetic moment and their total magnetic moment will be 0 over here. You can see the magnetic field, this H2O example. If you will count the number of electrons, hydrogen will have a 2, oxygen will have a 16, total number of electron will come in even number. NaCl also, sodium 23, chloride that will be 17. If we will add, we will get the even number of electron. Here also carbon, 6 carbon multiply by 12, 6 multiply by 1 and add it, you will get here even number of electrons. Here we will just compare the study or comparison of dimagnetic and paramagnetic substance. Here the diagram is very clear. You can have the first one, that is electron pairing. Just now we studied dimagnetic, no unpaired electron, or you can say all the electrons are paired. So if the pairing, all the electrons are paired and there is no unpaired electron, so that condition it is there for dimagnetic substance. But in the paramagnetic substance, the condition is at least they should have one unpaired electron or more than one unpaired electron, so that substance will come in a category of paramagnetic substance. Then spin alignment with a magnetic field. If outer magnetic field, the outer magnetic field alignment is this, then the dimagnetic substance electron alignment will be just opposite of this, and that's why that here we have written anti-parallel alignment or spin alignment with a magnetic field. But in a paramagnetic one, the magnetic alignment and the electrons alignment both are similar, and that's why we have written parallel spin alignment with a magnetic field. If dimagnetic substance we will keep near the magnet, then what will happen? Reaction to the magnet. These diamagnetic substance will be very weakly repelled by the magnet, but paramagnetic substance are going to be attracted by the magnet. Effect on magnetic field lines. Here if we will keep the diamagnetic substance, then field bend slightly away from the material. but here in the paramagnetic, field bends toward the material. So these are the general difference or the comparison you can say between the diamagnetic and paramagnetic. Important one is all the electrons are paired. Here one or more than one electron should be unpaired. Anti-parallel, and here you can see the parallel one condition. Here you can see the magnetic field, it is going to be repelled by the substance. Your magnetic field is going to attracted by the substance. Field bends slightly away from the material, and here it will be bends towards the material. Now we will have a next one, that is a ferromagnetism. A few substances like iron, cobalt, nickel, gadolinium and CrO2 chromium oxide are attracted very strongly by a magnetic field. Such substances are called ferromagnetic substances. Besides strong attraction, these substances can be permanently magnetized. In solid, the metal ions of ferromagnetic substance are grouped together into a small region called domain. This is a one new word will come here, that is a domain. What is this domain actually? In a ferromagnetic substance, the some grouped are there, means some particular group are there, and in that small region or group, that region in the ferromagnetic substance are called domains. And in one particular domain, the magnetic moment of all the electron will be similar. Thus each domain acts as a tiny magnet. In an unmagnetized piece of a ferromagnetic substance, the domains are randomly oriented and their magnetic moments get cancelled. We are talking about which one? We are talking about unmagnetized piece, means which one is not magnetized. So if such type of ferromagnetic substance we will take, and we will see the domains are randomly oriented and their magnetic moment get cancelled. But when the substance is placed in a magnetic field, all these domains get oriented in a direction of magnetic field and a strong magnetic effect is produced. This ordering of domains persists even when the magnetic field is removed and the ferromagnetic substance becomes a permanent magnet. It means such type of ferromagnetic substance, when they are unmagnetized, their domains are randomly arranged and their magnetic moments get cancelled. But when such type of ferromagnetic compounds we are keeping in a magnetic field, there all the domains will get aligned in a magnetic field or in a one line only or parallel to the magnetic field. And because of that, when you remove the outer magnetic field, that time also they will behave as a magnetic property or they will show the permanent magnet in them. Here you can see the alignment of domain. We have a three type of substance: ferromagnetic, antiferromagnetic and ferrimagnetic. These are the symbolized for the domain. Here you can see in the ferromagnetic substance, all the magnetic domains are aligned in a same direction, and that's why they will increase the magnetic moment and they will show a permanent magnet in them. In the antiferromagnetism substance, you will see the domains are arranged in such a way, or you can say domains are arranged in unequal way, that they will cancel their magnetic moment and the total magnetic moment of such substance will be zero. Here you can see one is up, one is down. So here total will be zero. Again one up, one down. The total magnetic bar or mu value will be zero. Here also the same condition. But in the ferrimagnetic, the last one you can have, the ferrimagnetic one, in which you can see the total magnetic moment will not be zero. Here 2 is up and 1 is down. Again 2 is up and 1 is down. So total they will not cancel each other, but some magnetic moment value will be there. And that type of substance, it is known as ferrimagnetic substance. Antiferromagnetism, substance like MnO showing antiferromagnetism have a domain structure similar to ferromagnetic substance, but their domains are oppositely oriented and cancel out each other magnetic moment. Ferrimagnetism. Ferrimagnetism is observed when the magnetic moment of a domains in a substance are aligned in parallel and antiparallel direction in unequal number, and they are weakly attracted by the magnetic field as compared to the ferromagnetic substance like Fe3O4, that is magnetite, and ferrite like MgFe2O4 and ZnFe2O4 are example of such substance. These substances also lose ferrimagnetism on heating and become paramagnetic, and the temperature on which this type of changes will be there, that temperature it is known as Curie temperature.